Hello everyone, I'm Norman Wildberger, and today I want to introduce the important notion of determinants, just a central theoretical concept in linear algebra. And well, there's also a lot of computational aspects to it. And it's connected with a lot of different things, and sometimes it's a little bit tricky to give a completely logically coherent account of determinants. Usually in linear algebra courses, especially sort of at the first year level, there's a bit of cheating involved, and I'm afraid I'm going to have to be guilty of that a little bit here too, because otherwise it would take a little bit too much time to develop some relatively serious algebra and even some combinatorics to lay out the whole story completely. But at least I'm going to be reasonably honest, and I'm going to point out where the difficulties are. So what is a determinant? Okay, so that's a good starting point. So a matrix A, which is square, say n by n, has associated to it a number, okay, called the determinant. So the determinant of A, it's expressed in a number of different ways. Sometimes we write determinant of A with a bracket. Sometimes we write determinant A without brackets. Sometimes we write A with an absolute value around it. Okay, so it's a number. Now, what's important about this number? Well, it has a number of interpretations. Before I tell you what it actually is, which is a little bit tricky, let me tell you, why we're interested in this number. This number is important for several reasons. The one that connects most directly with what we've been doing is that it turns out that A is invertible precisely when the determinant of A is not equal to 0. So the determinant is a kind of a test which tells us when a matrix is invertible. Another important reason is that the determinant of A can be interpreted as a scaling factor. When A is viewed as a linear transformation. Now I'm just writing this down here because we don't know what a linear transformation is yet. So we're going to explain this later in our second course, okay? But that will turn out to be an important aspect of it, that it's a scaling factor. It tells us how much a transformation scales areas or volumes. And a third important reason, which is connected with this second one, is that the determinant of A captures the signed volume of the n-dimensional parallelipiped, okay, whose sides are, say, the columns of A. So in other words, the determinant has something to do with signed volumes. So there's three kinds of, at least initial sort of motivations for introducing determinants. First of all, it has something to do with invertibility. It has something to do with scaling, or how much areas are transformed when you think of A as being a transformation. And we'll learn about that later. And it also captures the signed volume of a parallelipiped, which is a kind of an n-dimensional analog of a parallelogram. Now, that last one, even though in higher dimensions it's actually quite complicated, at least in 2 dimensions, it's quite understandable, and that's a really good place to start. So I want to talk about that interpretation now in terms of areas in the plane. All right, so let's look at the two-dimensional case and signed areas. So to do that, I better define what the determinant of a 2x2 matrix is. So if A is, say, the matrix A, B, C, D, then the determinant of A is AD minus BC. That's the definition, okay? That's a definition of the determinant of a 2x2 matrix. And we've seen that before. We saw that we had a formula for the inverse, and it was exactly this quantity that appeared in the denominator of that formula. So if that denominator is 0, then the formula doesn't work, okay? And we don't get an inverse. So it's sort of natural that this connects with invertibility. But I want to explain to you why it connects with areas. So let's cook up 2 vectors, which are, say, the columns. Okay, we'll think about the columns of this matrix. So here is a vector. Let's call it the vector, that's AC. And here's another vector. It's the vector BD. And what I'm claiming is that if you look at the parallelogram that's generated by these 2 vectors, okay, there's a parallelogram. So that means that this point up here, let's say this is the point A, and this is the point B, this is the point C. C will be the point with coordinates A plus B and C plus D. Okay. So the claim is that the determinant of A, this AD minus BC, is essentially the signed area of this parallelogram. Okay. So the area here, the signed area, is equal to AD minus BC. So I want to convince you of that. Okay, so I want to convince you that this purely algebraic formula has something to do with areas. And it's a very different kind of area formula from what you're used to perhaps in high school, because it doesn't, have lengths and widths exactly in it. So we could try to use some trigonometry and introduce angles and so on, but that turns out not to be really the best way. The best way perhaps is to, well, there's different ways, but let's do a kind of a simple, naive kind of thing and sort of look at various triangles and rectangles that are formed in this picture, okay? So if we want to get at that red area, what are we going to do? So let me prove this claim, okay? Proof. Let's call the red area, let's call it delta, all right? That's the area that we're interested in. Okay, so what is delta? Well, the way I've drawn the diagram, it's a difference between the big enclosing rectangle and various smaller ones. In fact, I could kind of make it more precise by drawing these things here. So you can see that what I've done now is I've decomposed this big rectangle into the parallelogram we're interested in, and then there's a couple of squares, and there's also 4 triangles. Okay, so the area of the parallelogram is going to be the big rectangular area, which is the product of color, which is the product of the base A plus B times the height C plus D, and I have to subtract some things. Okay, so let's subtract. How about this one here? What's the area of this little rectangle? Well, the base, because we're going from a x coordinate of A to a coordinate of A plus B, it's going to be B. Oh, sorry, it's going to be B. And the height is just C, so that's BC. And now let's also subtract the height of this little rectangle up here, okay? Its x coordinate is going to be that's BD, so B, and its y-coordinate is going to be the difference. That's C. Okay, and then there's these 4 triangular things. Now the triangular things, so this one here, for example, and this one here are going to be the same because they both have this hypotenuse, which is this vector here, which these 2 vectors are the same. So the 2 triangular pieces in green form a rectangle. Okay, so the rectangle is going to have side, the bottom is A, and the height is C. And then there's another one. Let's do it in blue, let's say. So this triangle and this triangle here, they don't look very much the same, but they're just 2 sides of a rectangle. If you put them together, they're going to be the same to give a rectangle with dimensions B, D. Okay, so we do all of that. What do we get? We expand the first thing out. We get AC. The AC cancels with the AC. We get a BC that cancels with the BC. We get an AD, which doesn't cancel with anything. We get a BD, which cancels with the BD. And we get still a minus BC left over. So that little cut and paste shows us or justifies this claim that this determinant is actually corresponding to a signed area. So this makes it look like the signed area formula, is actually a consequence of Euclidean formulas and base times height. But actually it turns out that when you start looking at the theory of area a little bit more carefully and generally, you realize that this is actually a more fundamental formula than the base times height formula that you're used to define the areas of rectangles. Okay, so there's some claim, okay, that this is actually a more fundamental notion of area. Now that takes some explaining, but if you are interested in that sort of the foundations of that, have a look at my Algebraic Calculus 1 course, okay, which is all about calculus, and well, it's calculus in a very general kind of way, and sort of hopefully in a precise way. And you'll see there that the entire theory of area, because in the integral calculus is all about area, can be sort of framed in a discussion that starts with this notion of area. So this turns out to be the fundamental notion of area that we can use to systematically build up a coherent theory of areas of curves. So yeah, it's a very powerful foundational tool. Now to go to 3 dimensions, okay, I will just show you the picture in 3 dimensions. In 3 dimensions, there's also a corresponding formula. So I have to tell you what the corresponding thing is, and it's a bit more complicated than this 2-dimensional one, okay? So let's say if A is a 3 by 3 matrix, let's write it as A, B, C, D, E, F, G, H, I. Then what is this magical determinant? So here's the formula for the determinant of A. It's going to be 6 terms. A times E times I minus A times F times H, plus B times F times G minus B times D times I, and plus C times D times H minus C times E times G. If you stare at this, you'll see that there are 6 terms, with each containing a single entry from each row and column. So for example, if we look at, say, BFG, that's that term times that term times that term. And indeed, those 3 terms, there's 1 in each row and 1 in each column. And all these 6 terms all have exactly that property. And in fact, these are exactly all of the terms that you can cook up from the entries that are formed by taking products of elements with exactly one in each row and in each column. And it's not too hard to see that there's going to be, in general, 3 factorial of those. So there's 3 factorial terms. These are the sort of number of ways of choosing one element from each row and column of the matrix. And so this is quite an imposing formula. Let's get rid of this thing. So let me put a box around it. So it's a very imposing formula perhaps, but it's also quite elegant. But it does show you that, calculating determinants is going to be potentially complicated, because this is only the 3-dimensional version, right? So the higher dimensional versions are more complicated. But I do want to at least give you an impression of what how you should think about what this number means, okay? So here is an interpretation. We're in 3-dimensional space. Let's look at the 3 columns of the matrix A. Okay, so those are 3 vectors. Maybe there's the vector A. What was A, B, C, D, E, F, G? So A, D, G. That's one vector. Another vector is the second column, B, E, H, B, E, H. And then there's a third vector, which is the third column, C, F, I. Okay, C, F, I. Now, these 3 vectors determine a parallelipiped, which is a 3-dimensional analog of a parallelogram. So let's say we take 2 of them, say these 2, they form a parallelogram. If we take these 2, we form a parallelogram. We form these 2, we take a parallelogram. Okay, and then we can sort of fill this thing out to something that looks like this. Okay, this is a parallelipiped, whose sides are all parallelograms. And the claim is that the determinant of matrix A corresponds to the signed volume of this parallelepiped. So in other words, we're talking about the volume, 3-dimensional volume of this box with slanted sides determined by these 3 vectors. And again, if you're going to go through and develop a theory of area or volumes in 3-dimensional space, it's actually quite subtle, okay? And it turns out, right, that this is actually the starting point, which is best. It's best to start with this as your notion of signed volume, and then show that this notion gives rise to a consistent framework of volumes that captures the intuitive properties that we would expect volumes to have. Okay? But that's a fair amount of work. Okay, that's a fair amount of work, highly non-trivial. But I do want you to have this idea in mind that determinants, at least in 2 dimensions and in 3 dimensions, represent volumes. You might also ask, just for completeness, what about the 1-dimensional case? We should also say that. So in the 1-dimensional case, suppose we have just a matrix A with a single entry. Well, then determinant of A is just the single entry A by itself. And in some sense, that's also a kind of a measure of extent. It's just it's like a 1-dimensional area or an extent. So here's the origin. Here's a point A, and we're talking about this vector. Okay, it's the vector A. Okay, and this number represents how big it is, but in a signed way, not in an absolute value sense. So it's not like a distance so much as a displacement. Okay, so it can be positive or negative depending on the value of A. Okay, great. So what is the official definition of a determinant? So the way we're going to do this is to use an inductive procedure so that at least we have a definition. And the inductive procedure is sort of consistent with the three cases that I've shown you now. Okay, so the definition is for the n-dimensional determinant is it's an inductive definition. Okay, so if A is an n by n matrix, say with let's give the elements some name. So let's say that A is, say, a matrix consisting of Aij, little aij. So that's the ijth entry of this matrix A. Okay. Then let's let A sub ij, capital A sub ij, okay, be the n minus 1 by n minus 1 matrix obtained from A by removing the ith row and jth column of A. So this is called a minor of A. Okay, so that's an n minus 1 by n minus 1 matrix. It depends on I and j. Then our definition is that the determinant of A is A11 times the determinant of A11 minus A12 times the determinant of A12 plus, and then alternating plus and minus till you get to the nth one. The nth one will be A1n times the determinant of A1n with a minus 1 to the n in front of it. So alternating plus or minus depending on whether n is even or odd. That is an inductive definition. And maybe I should say the determinant of A, which is also equal to A in absolute values, is given by the following. So this is inductive because the n by n matrix depends on evaluating n minus 1 by n minus 1 matrices. So an n by n determinant depends on n minus 1 by n minus 1 determinants. And so you can see that as n gets larger, the computational problem of calculating determinants from this definition is going to be a lot of work. So let me illustrate this definition, okay? So you can see that it corresponds with what I was doing earlier. So let's apply this to the example that we did before, but now we're going to use this determinant. So we'll stick with the same 3 by 3, A, B, C, D, E, F, G, H, I. According to the definition now, what should the determinant of A be? It should be A times the determinant of the matrix E, F, H, I. So notice that what I'm using here. So this, what's inside here, okay, is the matrix A sub 1, 1. Okay? It's what we get when we remove the first row and the first column. It's that little 2 by 2 matrix there, okay, obtained by removing the row and the column of the 1, 1 entry, which was A. So that's the first element in this sum. The next element is moving along to the second entry, which is B, and then we have to multiply by the determinant of the matrix that we get by removing the row and column through B. that will be the 2 by 2 matrix DFGI. So that's the minor corresponding to 1, 2, the entry B. And then plus C, the last term, will be times the determinant of the 2 by 2 matrix DEGH. All right, so this is the minor A12. This is the minor A13. So we're taking a linear combination of these three minors, each of which is itself a 2 by 2 determinant. Okay, and that linear combination gives us the entire determinant. So let's see what happens when we do that. So this 2 by 2 determinant is EI minus FH. This next one is DI minus GF. And this next one is plus C times DH minus EG. Okay, and if we expand that, we get AEI minus AFH minus BDI, or maybe I'll do the plus first, plus BGF minus BDI plus CDH minus CEG. And hopefully that's the same as what I originally told you was the definition up here. Okay, so this is then an inductive way of seeing how to go from the two-dimensional to the three-dimensional. And you can check also that this induction goes from the one-dimensional to the two-dimensional. But it also, at least then in principle, allows us to calculate higher dimensional determinants. So to calculate a 4 by 4 determinant, we would have to calculate 4 3 by 3 determinants and take the corresponding combination. So we have to talk about the properties of the determinant. Properties of the determinant. So, first of all, the determinant of the identity matrix is always equal to 1. The determinant of the identity matrix is also always equal to 1. 2, if you interchange or swap 2 rows or 2 columns, then the determinant changes sign. Changes sign. In other words, it becomes the negative of what it was before. Interchanging 2 rows, you multiply the determinant by -1. Or interchanging 2 columns, you multiply the determinant by -1. That was an elementary row operation, right? So what about the other elementary row operations? Third, if you multiply a row by lambda, then the determinant is multiplied by lambda. Fourth, if you add a multiple of one row to another, the determinant does not change. Another important property of the determinant is that the determinant of the transpose of the matrix equals the determinant of the matrix. Taking the transpose of the matrix doesn't change the determinant. And I want to mention one more property, which is related to the ones I've mentioned before, but it's sometimes called the multilinear property. It's not exactly a linearity in the obvious sense. It's a multilinearity that I will write it like this. If you have a matrix A, okay, and it say has the first column is say V1 plus V1 prime. That's the first column. And then the second column is V2. And then the nth column is Vn, okay? If A is a matrix whose first column is a sum of two vectors, but the other columns are just individual vectors, then the determinant of A equals the determinant of the matrix with just V1 and all the other columns the same, V2 up to Vn, plus the determinant of the matrix that has V1 prime, V2 all the way to Vn. So this is linear, so the determinant is linear in the first column, and in fact it's linear in any column because the swapping property above shows that that's going to happen. So the determinant is linear in any column or in any row, as it turns out, or in any row because the transpose has the same determinant. Okay, so that's sort of a bunch of properties. What about sort of like proving or understanding these properties? Well, the thing is, our definition is complicated. It's not so easy to prove all of these things in general, but we can prove them or demonstrate them for the 2x2 case and the 3x3 case. And for most applications, having to do with ordinary geometry and in three-dimensional space, 2x2 and 3x3 determinants are, what you meet a lot of the time. So it's actually nice to have, direct verifications of the two-dimensional and the three-dimensional properties directly, because we have these very explicit formulas for the determinants of 2x2 and 3x3 matrices, so that you can see the various properties. So for example, here is the 3x3 property of the determinant, and if we look and think about how does this dependent on the first column, A, D, and G, then you see that the A, D, and G, there's an A here, there's a G here, there's a D, there's a D here, there's a D here, and there's a G here. Each one of these terms has exactly one element from that first column. So this is the reason why this thing is linear in the first column. So if we, if we say multiplied the first column by 2, okay, then all of these entries would multiply by 2, and the entire determinant would multiply by 2. Or if we replace this first column with a sum of two columns, then the entire determinant would be the sum of the two corresponding determinants. Which makes me think I should probably also, this multilinear property, that's sort of one part of it. The other part is also that if I take the determinant of, say, C times V1, so if I multiply the first column by, say, C, and take the determinant, that what I'm going to get is I'm going to get C times the determinant of the original matrix V1 through Vn. And this works for any column. Works for any column and any row. Consequence of that, which is actually quite useful, is that if you multiply the entire matrix by C, the determinant of C times the entire matrix, okay, that means you're multiplying the first column by C, you're multiplying the second column by C, you're multiplying the nth column by C. Each one of those individually is going to multiply the determinant by a factor of C. So altogether, you're going to be multiplying the determinant by C to the n. So the determinant of C A is equal to C to the n determinant of A when A is n by n. Okay, so those are some sort of abstract properties. In our next lecture, we'll talk a little bit more about some of those properties and verify some and get more experience with actually calculating determinants so that you can see these various properties in action.